All right, today is going to be reviewing for the exam. Sometimes I do go sort of like backwards through the content, but I think this time we're going to go forwards through the content. And we will still try to break things up into 2 lectures. What did we cover through on the last exam? We covered through the basics of mass and density problems. After that first exam, we started more complicated mass and density problems, for example, trying to figure out the center of mass of a triangle sheet of metal. We figured out the mass of the atmosphere above the Earth up to, 100 meters or something. So those are more complicated mass and density problems. Got into other kinds of physics, work done by a force and pressure problems. Got into a little bit of finance, present and future values. Did more probability, including actuarial applications, and then we went into sequences and series. Now that's sort of a real broad overview. Let's go into more depth on things. Let me start by thinking about the kind of problem where you are trying to find the mass of some sort of spherical region. In fact, we can look at one of the practice problems. Maybe that's partially what we'll focus on here. Stop. There we go. This time, it's not actually a mass you're trying to find, but the number of stars in a spherical region. Can you see this okay? Zoom in if you need to. Rho of R is a density in stars per cubic light year. Cubic centimeters, maybe about this big. Imagine how big a cubic light year is. Okay, a light year is how far light can travel in 1 year, which is really, really far. Light travels so fast it can go around the Earth like 7 times in 1 second or something. That's how fast light goes. How far does light go in a year? Really far, though the nearest star is like 4 light years away or so. This density is giving us the number of stars per cubic light year in something called a globular cluster. Globular cluster, which is sort of like a mini galaxy, if I understand it right. What do we want to find? We want to find the number of stars. That's analogous to being given the density, a mass density, for example, in grams per cubic centimeter of a 3-dimensional object, say, and trying to figure out the mass. It's an analogous thing. This is more of a population kind of application. It's the spherical distribution of stars. So this is a 3-dimensional sphere here. And you'll notice this density is a function of r being the distance from the center of the sphere. The entire sphere might have a certain radius, capital R. I guess we're taking it to be 100 light years for the entire radius. 100 Ly stands for 100 light years, which is a distance. We're assuming the density only depends on how far you are from the center. So for an interior point inside the sphere, how far is it from the center? Call that R. Try to imagine that 3-dimensional maybe coming out of the board towards you. The density of stars on such a sphere, essentially, of maybe a very small width, is essentially constant. That's the idea here. Is that really true? Probably not, but it's a modeling kind of thing. And when you've got enough stars, it might be a pretty accurate model. I didn't come up with this model, I just copied it from somewhere, so I have no idea how accurate it is. But the fact that it's constant on spheres of a given distance to the center means you can do this as a single integral instead of a triple integral. You can try to imagine slicing the big sphere into smaller spheres. That gets kind of hard to draw. I'll try to draw a smaller sphere inside here, but you need to use your imagination and imagine this 3-dimensionally. that sphere is inside the bigger sphere. They're both centered at the same point. And the radius of this sphere is supposed to be little r. Now I'm slicing it into thin slices, so in fact that sphere is not just a shell, it's got a little thickness to it. Call that thickness delta r. That gets even harder to draw. You've got to imagine a thin shell, essentially, of thickness delta r. Now we're talking light years for the units here. What could delta r be? It could be really tiny. It could be, I don't know, a few centimeters or meters or something. That's how small delta r could be compared to a light year. Or, you know, as a practical matter, it could be a lot bigger and still probably gives you a pretty good approximation. But we don't worry about it. It's just a very small amount. What is the volume of that thin shell of a sphere, so to speak? You might call that delta V. Now we know the formula for the volume of a sphere is 4/3 pi r cubed. But it's going to turn out we're not going to use that. We're going to come up with an approximate volume that leads to the integral that we want to do more quickly. You might wonder, is this approximation justified? And it turns out it is. I'm not going to explain it. But it turns out this approximation is justified and gets us to the answer more quickly. Take the surface area of the sphere, 4 pi r squared, and multiply times the thickness. That's the approximation. 4 pi r squared is the surface area of the sphere. Multiplied by the little thickness, you get an approximation to the volume, not of the inside of the sphere, but of the shell with delta r. It's not exact, it's an approximation, but it gets better and better as delta r goes to 0. And it does get us to the integral quickly, and it can be justified in other ways.
So using like the surface area, would that apply to other shapes as well, like a cube and things like that?
Yeah, I mean, if you were doing a cube,
it might be easier to do it some other way.
It probably would be easier to do it some other way, but yeah, I mean, it does apply to disks.
Okay.
For example, you had a homework problem, I believe, where you had a population of a city that was a disk shape that was dependent on the distance from the center of the city. And there, the thin shells become thin rings. Now, and you approximated the area of the thin ring by doing the circumference times delta r in that case.
Right.
So this is the surface area times delta r. That's the surface area. What about the mass? Well, not the mass, but the number of stars in such a thin sphere. We're after the total number of stars. The approximate number of stars, what should I call that? Delta n, maybe? For number of stars? It's a little bit funny. I mean, if delta r really is just a centimeter or a meter, and you are considering such a thin disk, could there be any stars inside there? And of course, stars are much bigger than a centimeter or a meter. So it's a little funny that way. Maybe delta r should be more on the order of millions of kilometers or something, billions of meters. It still would be very small relative to a light year. Take the density, number of stars per unit volume times the volume. This is approximately rho of r times delta v, which is approximately rho of r times 4 pi r squared times delta r. Or you can plug in the formula for rho of r if you like. Adding up things like this would give you a Riemann sum approximation to the total number of stars based on some partition of the distance from the center of the sphere to the edge, delta r being maybe 0.1 light years. If delta r were 0.1 light years and you're going out to 100 light years, you'd have 1,000 terms in your sum. Since 100 divided by 0.1 is 1,000. When you're asked for the Riemann sum, you essentially can just take this and put a summation sign in front of it, and we'll go ahead and be sloppy and not worry about what the sample point is, and not even bother putting index of summation on it. Is it okay if I don't write that? When you're asked for the Riemann sum, just put a summation for sign in front of it. And you don't even have to bother with the formula in it. You would need to bother with the formula to do part C, if you look back up here, which says evaluate your integral. Back over here, your integral is going to look like this. Units of light years for distance. We go up to 100 light years. Let me go ahead and put the formula for rho of r in here. And let me simplify it a little bit. R over 100 quantity cubed is r cubed over 100 cubed. 100 cubed is 1,000,000. And this integral is not as hard to do as it looks. You could do it with substitution. W equals 1 plus r cubed over 1,000,000. dw is 3 over 1,000,000 r squared dr. R squared dr would be 1,000,000 over 3. dw, you could put that in place of the r squared and the dr. You would want to change your limits of integration if you do this in terms of w. When, just a second, when r is 0, w would be 1. When r is 100, w would be 2, it looks like. 100 cubed is 1,000,000, divided by 1,000,000 is 1, plus 1 is 2. Question?
Regarding this type of question and others that have integrals, would you want us to do integration methods for all of them and not use our calculators to integrate such thing?
You should be able to do the integral by hand, yeah, if I ask you to. I might ask it in phrase it, I might phrase it as give me an exact answer.
Okay.
And all your pi, and then you really need to do the integral by hand. So yeah, you should review substitution and integration by parts as sort of the main techniques that might be necessary. Separation of variables, sometimes you need partial fractions, but I don't think I'm going to give you any partial fraction problems. And I think I would also avoid any trig substitution problems. So focus mostly on substitution and integration by parts if you want to practice your rules. So doing the integral is not too hard here. It would be doable. The fact that you got the r squared there makes you think that the people who did this modeling of the density of stars purposely picked a cubic of a simple form so that they could actually do the integral. That might have been part of their motivation. It really shouldn't be their motivation, but I don't know, I'm just guessing that maybe it was so that they could get a nice integral. Okay, I'm not going to bother doing it. You can do it. I do have the answers on the rule, so you can check it there. What else? There's center of mass. I think for a center of mass, I'd give you a simpler situation. Technically, center of mass showed in the last exam in the case of thin rods. But I might give you, well, it could be a triangle. Say an isosceles triangle with base 10 and height, say 15 or something. Situated in a coordinate plane with an x and y axis like this in such a way that you've got a formula for the density as a function of just say x, for example. To keep things simple, I did introduce you to multivariable calculus a little bit with those double integrals. There will not be any double integrals in your exam, though. You can introduce the idea. We might be just after the x coordinate of the center of mass. X bar. It's a ratio of two integrals. The bottom integral is the integral that gives you the mass of the object itself. Integral of delta of x itself. From A to B. And the upper integral is going to give you the moment in the x direction. Actually, it's a little tricky for a triangle. Maybe I should do a triangle. Okay, let's change it to a rectangle. Rectangle of base 10 and height 15. The moment in the x direction is going to be given by that. Keeping things as simple as possible here.
So remind me what delta x is.
Delta x is the density. Density, saying mass per unit area of a thin plate.
Okay.
That would give you the center of mass in the x direction. Try to keep things as simple as possible if I give you a problem like that. What other kinds of physics comes up? Again, I mentioned work done by a force and pressure, force and pressure, water pressure. The two situations, there were three situations where we considered work done by a force. One was a mass on a spring. I think I will not put that on the test. Another situation was like hauling a chain or a rope upward against gravity. And a third situation was pumping water out of the pool. I think those last two would be the situations that I would give you a question on. As possibilities. Probably not both of them, but one or the other. In the situation where you're hauling a rope or a chain up against gravity, say up the side of a building, so you're standing on the top here, hauling something up, maybe there's a mass down there. The rope or the chain has a certain mass density. It's a linear mass density. Maybe 0.5 kilograms per meter might be the density of the rope or the chain, mass density. And this thing down there has got to have a certain mass, maybe 10 kilograms. You're trying to find the total work to haul both the rope or chain and the mass at the bottom up a certain distance. Say this distance is 100 meters. How much work do you have to do? What's the force? You're doing work against gravity. As far as the mass at the bottom goes, it's got to go the full 100 meters, and it stays the constant mass. In that case, in that situation, the work done is just the force times the distance. The mass is 10 kilograms. The force, meaning its weight, would be 10 times 9.8, because you've got to multiply by the acceleration due to gravity to get the force, times the distance of 100 meters. That product, which would be 9,800, is the work done on the mass at the bottom. That would be in joules. Work has same units as energy, joules, in standard units. If you're using English units, units for work are foot-pounds, but in standard units it's joules. As far as the rope or the chain, you've got to imagine breaking it up into small pieces, say of height delta y. That's its height or length of that small piece. The weight of that small piece, which would be a force, you could call delta F, would be approximately, or exactly actually in this case, 9.8 times 0.5 times delta y. There's the mass of that small piece, 0.5 times delta y, because we have a mass density. 9.8, the acceleration due to gravity needs to come into play to make that a weight, a force. Weight and force are synonyms. But then the distance depends on y. It's the distance that is really changing for different pieces of the rope. The rope is a uniform density, but how far it goes changes. The work done to take that small piece and bring it to the top is approximately delta F times y. That's an approximation because y is technically not constant over this entire little chunk. But approximately, if it's small. Again, this is delta F right here. 9.8 times 0.5 would be 4.9. This would become 4.9 y delta y. And your integral would be then of 4.9 y. Integrating, y goes from 0 to 100. So this would give you the work done in joules for hauling the rope or the chain itself against gravity. 4.9 comes from 9.8 times 0.5 right there. The 9.8 is the acceleration due to gravity. The 0.5 is the mass density. 0.5 times delta y, that's the mass itself of the little chunk. The weight of the little chunk, which is a force, is this product times delta y, which is 4.9 times delta y. Then multiply that by y. That leads to an integral to give you the work done for the rope or chain itself. And then add the two answers at the end to get the final answer. For pumping water out of pools, the pool could be a box shape, it could be a cylindrical shape. I think the practice problem one I made was a cylinder. You've got to slice it into thin slices of width or height delta y. I think the book typically calls it delta h. Doesn't matter. Figure out the work done to pump that thin slice of water out of the pool, ignoring molecular effects, ignoring the fact that your pump, the hose goes down to the bottom, so the water molecules are going down first before they go up. You sort of ignore all that stuff. And evidently you can justify that you can imagine that you're just pumping thin slices of water up. What distance? The distance you've got to pump it upwards is y. What's the weight? The work done will be the weight of that thin slice times delta y, or times y. Well, delta y is the thickness. If we're dealing with the cylinder here, the cross-sectional area is pi r squared. You've got to know the radius. Pretend the radius is 20 meters. That would be a big tank. Oh well. 20 meters for the radius. Pi times 20 squared. Will give you the area of the cross-section. Multiply that times delta y and you get the volume of the cross-section. The practice problem is not in standard units, not in SI units. The practice problem is in English units. So maybe we should focus on that. Remember where it is here. Oh, I guess it's right here. Feet for distance. And pounds for weight, which is a force. The weight density of water is 62.4 pounds per cubic foot. You're going to need that to get the weight of this thing. This is, again, its volume. Multiply this by 62.4 to get its weight, which is a force which already contains gravity in it. You don't need to multiply by g here. G is 9.8 meters per second squared in SI units. It's about 32 feet per second squared in English units. But with the 62.4, that's already factored in. The acceleration due to gravity is already in that quantity because that's a weight density, not a mass density. So I mean, the English units are actually a little easier because you don't have to worry about g. That would be the approximate mass of that thin slice of water, to get the work done for this thin slice multiplied by y, add up things like that to get a Riemann sum approximating the total amount of work. In the limit, as delta y goes to 0, the exact work will be an integral of this stuff except the delta y becomes a dy. So you get 62.4, 20 squared is 400, times 400 pi y dy. If the tank is full to begin with, you could let y go from 0 to however tall the tank is. If the tank's not full, maybe it's only full up to here. Let's say the entire distance, well, maybe let's say it's full up to here so it goes better with the picture. The entire distance, the entire height there might be 30 meters, but the depth might be 25 meters. If that was the case, your limits on the integral would actually be, with this setup, y would go from 5 to 30. Because the topmost slice, I don't know if you can make sense out of this picture, the topmost slice of water would go up by 5 meters, and the bottommost slice would go up by 30 meters. So the integral would be from 5 to 30 in this situation. If the entire height is 30, but the water's only up to 25. Oops, I guess we're doing feet here, sorry. Mixing up my SI and my non-SI units. Okay. What next? Economics. Present and future values, which I don't yet have a practice problem related to this, and I realized after I made a couple new practice problems this morning that I need to put some practice problems like this on the list here, so I still have to update this file yet more. The present and future values in Chapter 8 don't involve any probability. There's nothing actuarial about them. You don't have any lifetime random variables involved. You have definite payments, definite annuities or income streams that you're thinking about. They could be discrete in nature, say equally spaced in time, maybe 1 year at a time. Certain payments that could start at the present or could start maybe 1 year in the future. You get $100 there, $100 there, etc. For the present value, you pull those all back in time to the present, so to speak. That's the way I imagine it. I think it's a good way to imagine it. If the going interest rate is, say, 2%, and we use a continuous interest rate, we interpret that as a continuous interest rate, which we can do if we want, then the present value of this amount, this $100 1 year in the future, would be 1,000 e to the negative 0.02 times 1, for extra emphasis, because it's 1 year in the future. The present value of the second one would be 100 times e to the negative 0.02 times 2. The present value of the third one would be 100 e to the negative 0.02 times 3. The present value of the fourth one would be 100 e to the negative 0.02 times 4. Add those present values together and you get the present value of the entire annuity. And it's a geometric series, a finite geometric series. You can add these numbers up, but what if you had 20 of them? You'd want to use Chapter 9 information about geometric series to figure out the sum, which I will talk about in short order here. For future values, again assuming we're doing continuous interest rates, 2% per year, maybe the future value at time 1, 2, 3, 4, then you'd have to take the amounts and push them forward into the future. This $100 here would get pushed forward 3 years. So its future value at time 4 would be 100 e to the positive 0.02, not negative, positive 0.02 times 3, because it's getting pushed 3 years into the future. And the future value of this $100 would be 100 e to the 0.02 times 2. And the present value of the third $100 would be 100 e to the 0.02 times 1. It's only going forward 1 year in the future. And the present value of the last one is just 100 because it's at the moment we're thinking about the present value for. We can think about, or the future value. We can think about the future value at any moment in time we want. I'm thinking about it at time 4. Then you add these together to get the total future value. For income streams, cash flows, instead of having discrete payments, you're having a continuous payment. You got a graph of some function of time that's telling you how fast the money is entering your bank account, say in dollars per day, or dollars per month, or dollars per year, or millions of dollars per year if you're lucky. It's a rate of money flow per unit time. Let's just say $1 million per year. You know, if money's coming into your account at a certain instant at a rate of $1 million per year, you know, the 365 days in a year, so it's like $3,000 per day approximately. Over the course of 24 hours, it's going to be a bit more than $100 an hour, a bit more than, almost $2 a minute, say, or maybe about $2 a minute, which translates then into what? How many every second? 120 seconds in a minute, divided 2 by 120. It's around 2 cents a second, is that right? I don't think so, no. Was it 2 cents a minute? I lost track of what I was doing there. So, I mean, you can imagine money coming in constantly with these flows here, right? And the rate could go up and down. Maybe it's coming in at $1 million a year at one instant, but then 2 hours later it's coming in at $2 million a year. The rate at which the money is flowing through these electronic accounts could vary. Of course, the simplest cases would be if f of t is horizontal or some other linear function. That would be the simplest case. The present value of such a cash flow from time 0 to time m, the book writes as this: the integral from 0 to m of the function f of t times e to the negative rt dt, where r is the given continuous interest rate as a % per year. Notice the negative sign there. We're pulling these back to the present, so to speak. You do have to derive this by imagining chopping up the time interval into little tiny pieces with delta t, and asking how much money do you get during that little time interval and pulling that back in time to the present. And the future value can be done as an integral from 0 to m, f of t times e to the positive r times m minus t dt. M again is just the moment you're ending the income stream here at. We want to find the future value now at time m. You got a positive r because you're pushing the amounts into the future instead of pulling them back into the past. M minus t is there because at a given moment in time t, the distance to push that amount forward into the future is m minus t, that distance right there. That's why the m minus t. Okay, but as far as the exam goes, you just got to use those formulas. You got to recognize what kind of situation it is and use those formulas. Again, I don't have any practice problems about that yet, but I will work on that this afternoon. Probability and actuarial stuff comes next. I did add an actuarial problem here for the practice problem this morning. Let's take a look at that. And I think what I'll do is I will make your actuarial problem similar, though maybe with less work. Maybe I'll give you more information than I do in the practice problems here. After we look at this, we'll take a short break. Actually, maybe we should take our break now. Okay, let's take our break now.